Hello everyone from the University of Buraimi in the Sultanate of Oman. This is a presentation for a graduation project titled Energy Analysis of 1 Gigawatt Thermal Power Plant by 4 mechanical engineering students in the University of Buraimi, Mr. Ahmed Arman, Mr. Marwan Al Saadi, Mr. Ahmed Al-Maqbali and Mr. Sulaiman Al Sharji. The project is participating in the 9th undergraduate virtual research competition by Abu Dhabi University with a research ID of 6971. Here are the contents of the presentation. There are 9 topics in 9 slides. The first one is some energy and power units. So let's go to that topic. Starting with some units for the power, whether it's electric or shaft power. The International System of Units use the watt as the unit of power. We also have the kilowatt, which is 1000 watts, and 1 kilowatt is approximately the power needed to operate a small kettle. We also have the megawatt, which is 1000 kilowatts, and we have the gigawatt, which is 1000 megawatts. Some units for energy, whether it's electric or thermal, include the joule, which is used in the International System of Units. We have also the kilojoule, which is 1000 joules, and we have the gigawatt hours, which is 3.6 times 10 to the power 12 joules. This is a large energy unit. This amount of electricity is enough to operate an air conditioning unit for about 30 years. This graph shows the production of electricity in Oman over 6 years. And although there is seasonality in the profile, being low in the winter but high in the summer, it seems there is an overall annual trend of increase. And this suggests more demand on electricity. But how does this electricity come from? The electricity generally comes from power plants or power stations, which generate electricity in large quantities. And Oman relies heavily on power and natural gas as the primary fuel for its power plants. This photo is for one of the power plants in Oman called Barka 2. It has a power level of 678 megawatts. Now this can lead to the aim of the project. The aim of this project is presenting a simple design of a power plant using water as the working fluid. Our target is to produce 1 gigawatt of electricity or 1000 megawatts. This is enough to cover about 66,000 homes in Oman, assuming that each home has a peak power demand of 15 kilowatts. This is enough to operate about 4 air conditioning units plus other electric devices at home. This sketch shows the 3 components of the power plant. A typical thermal power plant. We have subsystem A or section A, where the heat is generated, for example here by burning fuel with air in a furnace, and the exhaust gases go out to a stack, and the heat is delivered to subsystem B, which is the Rankine cycle. But you don't need to burn fuel. You can use a clean energy source like nuclear reactor, or you can use solar heating. But anyway, in subsystem B, which is the Rankine cycle, we have 4 devices: the pump, boiler, turbine and condenser, and the water is circulating in these 4 devices in a cycle. So the pump pressurizes the water and sends it to the boiler. The boiler takes the heat and adds it to the water to become very hot water vapor or superheated steam. And in the turbine, this steam rotates the shaft of the turbine, and the output it leaves the turbine as a steam but mixed with some liquid water, and in the condenser any steam is condensed and converted into liquid water, which is suitable to be sent to the pump again. And the shaft rotating by the turbine is connected to the shaft of an electric generator in subsystem C, and this produces the electricity, which is the important output from the power plant. Now the more details about the Rankine cycle. We have here 4 devices and 4 states. State number 1, before the pump. The pump takes input work and pressurizes the water to state number 2, high pressure here. And then the boiler takes input heat and add this heat to the water. So you have state number 3, high pressure and high temperature steam. Now the turbine extracts energy from that steam and produces output work, and convert the steam to state number 4. and the condenser releases heat from that steam and converts to 100% liquid water, state number 1 again. This table number 1, shows a summary of the 4 processes in the Rankine cycle and the corresponding devices. We have the compression in the pump. So the low pressure and low temperature liquid water, state number 1, is converted into high pressure but still low temperature liquid water, state number 2. State number 2 goes to the boiler and a process of heat addition happens, and this water becomes high pressure and also high temperature steam, state number 3, which goes to the turbine where a process of expansion happens, and this water becomes low pressure and low temperature liquid vapor mixture, state number 4, which goes to the condenser and a process of heat rejection happens, and this water returns back as it was, state number 1, low pressure and low temperature liquid as it was before the pump. Here is the methodology. We have the assumption of steady flow, no change with time, and also neglecting changes in potential or kinetic energy, focusing only on the energy content and thermal and pressure energy through the specific enthalpy represented by the simple small h here. So the work input to the pump results in an increase in the specific enthalpy from H1 to H2 of water. The input heat to the boiler results in another increase in the enthalpy from H2 to H3, and in the turbine there is a drop in the specific enthalpy from H3 to H4, resulting in an produced work from the turbine, and in the condenser there is another drop in the specific enthalpy from H4 to H1, and heat is released Q out. The overall cycle analysis shows that the net useful work per kilogram of water, W net, is work W out, with the work from the turbine, minus Wn, the work consumed to the pump, and thermal efficiency is the useful work divided by the input heat. These values are per kilogram of water. Now here are the results. This table number 2 shows the 4 states, the properties of water in each of these 4 states. State number 1, we have saturated liquid water with a temperature of 50.2 degrees Celsius and the pressure is 0.125 bar or 1/8 of a bar, which is approximately 1/8 of a standard atmosphere. It's a very, very low pressure, and here H1 is shown here. State number 2 is compressed liquid. The temperature is still low, but the pressure has increased 400 times to 50 bar, and H2 is shown here. State number 3, we have superheated steam, the high temperature 600 degrees Celsius and high pressure 50 bar, and H3 is very high, the highest level in the cycle, 666 kilojoule per kilogram. And state number 4, after the turbine, we have liquid vapor mixture, 89% vapor and 11% liquid. Temperature and the pressure are low as they were before the pump, and H4 is shown here. So the drop from H3 to H4 is what produced the useful work from the turbine. The cycle thermal efficiency is 38.6%, and this can be improved, for example, by adding a second turbine. So we have 2 turbines working together in series, but this is beyond the scope of the project. That was the end. Thank you for watching.